Hi everyone, my name is Ivailo and welcome back to one of our daily stand-ups. Uh, and we're also joined by Nelson. So Nelson, good morning.
Good morning, Paolo. Good morning, everyone.
Very nice to be back. So Nelson, in this stand-up, we want to share what we did in the last several days, and we just want to give several updates about what we currently do. So if you don't mind, can you please give us a brief overview about what we did and what did we close in the last several days?
Sure. Yeah. It was a complicated uh, week, let's say. Uh, we found that some problems in one of the documents that we were reviewing to scan the junction conditions correctly and to apply them. Well, we solved those problems. Those problems are related to the fact that it's not it's not just straightforward always to write down the equations that we use. And if we found that there are what we call the junction conditions for the energy momentum tensor, there was a problem, and an additional term was needed. And we found that, and we solved that. Also, currently we are working on two things. I mean, one of the things I'm doing by myself, it just was reproducing all the calculations of Natario and reviewing the, the propositions and theorems that he has. And one of the things that I found there was just in order to, I mean, I did follow the propositions. And then I found out that this we call your proposition. I think this was point 1.6, and this is related to what's called like expansion volume element there, and it's this a term that appears in the metric, and it's basically where all the warp effect starts. So to understand this correctly, at least for me and for the team, it was necessary to correctly use and implement the second fundamental form, which is something that we have been studying for the junction conditions. But it appears here. What is this second fundamental form? Is the extrinsic curvature, and I don't know if I explained before what extrinsic curvature is, but it's the curvature that you see, I mean, roughly speaking, of a surface that is embedded in another space and with a higher dimension. We can think of this, for example, the sphere. You have a sphere, and you live on the surface of the sphere, which is something that we can imagine because we live on something like more or less the sphere that is the Earth. And you don't see the curvature of the Earth. It's not straightforward to see the curvature. You feel like you're living in something flat. So extrinsic curvature gives you an idea how this curvature it really is once you realize that you are not just on the surface. And this surface where you live is also embedded in the uh, a more wide and more greater, larger is the word space, and in this case, and then you see like an additional coordinate that is basically the coordinate that goes from the surface of the Earth out to space. Um, this is like a way of thinking in this extrinsic curvature. So the expansion volume element here appears as fundamental. So I started to review it, and I found that there are some issues when you work in the literature with this extrinsic curvature. There are like two or three ways to define it, and I was not completely sure about if each of them is the same or are some independent ways. Anyway, what I'm doing is I went to a specific sample. I'm following a very interesting lectures from Caltech. In this, he shows that there are some results that you can find to calculate this uh, expansion volume element, which is basically the trace of the extrinsic curvature. So what I'm doing right now is implementing this in a mathematical notebook just to simplify the calculations and find for the Friedman-Rosen-Walker model this results. So I can check that this is working correctly. Then I will check it again with Schwarzschild, and then I can apply safely for any. I'm trying to make a general approach to any space-time that we find that we can define an hypersurface, and from there define calculate the extrinsic curvature in this case. Also, the other part of the team is working on using again second fundamental form, which is the I think the other ticket that we have there.
So apologies.
Uh,
For clarification,
yeah,
when you
sure.
say this, the second fundamental form, this is us trying to understand how the space-time behaves on the surface of the warp bubble, correct?
Yeah, it's like I think that the most simple way of thinking of it is that if you have this bubble or any surface in general relativity or geometry, it's like how is how's the curvature of this bubble, for example, seen by an external observer that is outside of the bubble. It's a way of saying. But also we have another curvature who has intrinsic curvature, which is completely different. But yes, in a sense, it's that.
Okay, just wanted to make sure. All right, so please go ahead. You were saying about the task which Gabriel took.
Sure. What Gabriel is doing is, in fact, is he took again because we're learning this. He took a well-known example of junction conditions, and this now example, there's soft problem with some asymmetries in the energy momentum tensor between the that relates the space time that is outer space-time and the inner space-time. You have some asymmetries there. You have anisotropies. And in this case, what the known example work out the junction conditions by looking into the projections of the energy momentum tensor on the normal vectors to the surface, which are found using the well, we are they are very fundamental. Let's say they're fundamental for all and all kinds of junction conditions that you can use. But in this case, they use it, and with this projection of the energy momentum tensor, you uh, you demand some continuity conditions that which are going to translate into the junction conditions. That's an approach. What Gabriel is doing is redoing this example, but without using the energy momentum tensor conditions. He's just using first and second fundamental form to make the match only by thinking in the space-time itself. So in that sense, we don't need matter to be there. We just want to know how to match these space-times without needing to use any tensor matter tensor. So in that sense, he's using first fundamental form is a way of saying that you want the elements or the components of the matrix to be equal when you evaluate on the surface. And the second fundamental form, as I said before, is different. It's related to the extrinsic curvature, and you also want, in this case, a matching of the extrinsic curvature when you calculate that, uh, thinking that the outer surface is the one where your surface is embedded, and the other one is like a different pointing vector. Instead of having a sphere, for example, and you have a pointing vector that's going outside the sphere, then you have a pointing vector that goes inside the sphere, and then you have another space-time inside of the sphere, and then you have a different extrinsic curvature that is related to the space-time that you have inside the sphere, and you match both things together. And these are more related to the second, so the derivative of the metric, and it's a bit more complicated, of course, to calculate. And he's working on that, so we can compare both results, and we expect to find, of course, the same, and to have all these results by this week.
Excellent. Thank you, Nelson. Is there anything else you want to add?
Well, for the moment, no. The thing's very exciting because after I finish, for example, working on the Friedman Roadster Walker example, and everything is okay, it's going to be the next step. We're going to get in the, I think, the most interesting part of this, which is, and I will share it with all of you later. What is it that makes these metrics interesting for warping, to make the warp drives? And we were getting there, and it's going to be very exciting because we are getting really into the real problems. I mean, this is something that you can calculate. There's no problem in calculations, but the interpretations are quite hard, and we're getting there.
Of course, we're going to keep our listeners updated about our findings and everything we learn. All right, well, Nelson, thank you very much for this talk this morning, and thank you very much to everybody who is listening this podcast and daily stand-up. And if you feel like supporting us, you can do this on Patreon, and you can like or share the video, and please subscribe. And with that, let me wish to all of you to have a very nice and successful day.